Okay, let's get started.
I wasn't I wouldn't suspect you.
Okay. So this is, in some sense, just for your entertainment or your mental stimulation. You know, it will not show up on the exam, except possibly as a bonus problem. So then, you know, and that's not even, I haven't even decided that yet. So it may or may not show up on the final. Okay. But if it does, it will just be a bonus problem. Okay. So this course is your last course in single variables, right? If you go on to take the next course, excuse me, it will be multivariable calculus, or if you're doing linear algebra, that will be, you know, also, you know, very multivariable. And so, you know, what that will be about is not R, right? So up until now, we've been talking about the real numbers, but from here on in, it's basically in Rn. So Rn, what we mean by Rn is things that look like this: x1, x2, xn, where all of the components are real numbers, right? In other words, you have what's called an n-tuple, n-tuples of real numbers. This word tuple is, you know, from triple, like double, triple, quadruple, right? So n-tuples of real numbers. Right? They're also called vectors. Right? Real vectors. And I don't know what's with my throat, but so the way you want to think of these is that they're an extension of your normal numbers, right? You were dealing with numbers before. Now we're dealing with these things. They're just, you know, bunches of numbers, you know, and 3 numbers or 4 numbers or however many numbers. And so you'd like to do with these things what you do with numbers, right? You want to be able to add them. You'd like to be able to multiply them. You'd like to, you know, if you could, maybe you could divide them. Right? In linear algebra, you'll be thinking about, you know, what does it mean to have a matrix of numbers, say, and what does it mean to divide by a matrix? Can you divide by a matrix? Does it make sense? So you want the basic algebraic operations. Okay, and so for example, you want vector addition. Right? You want to be able to add these guys together. And it turns out that the right way to do it is you say, if you have x1, x2 through xn, and you're adding on another number, y1, y2 through yn. So you have two vectors and you want to add them together. It turns out that the sort of most profitable way of defining addition is the obvious one. You just add them component by component. You say x1, y1, x1 plus y1, excuse me, x2 plus y2, x3 plus y3, etc., etc. xn plus yn. Okay. So for example, in R2, if you have some vector AB, you have some point AB, you have some point AB, and you have some other point CD, then the sum is going to be what you get if you add the x components together and then you add the y components together. And what that, right, so you have this x component plus this x component, this y component plus this y component, right? And what that boils down to pictorially is, some of you probably know this already, is that if you drew an arrow from here to here and you drew an arrow from here to here, then the sum would be the point that you get when you take this arrow and add it onto the end of that arrow. Okay. So this point here, sort of obviously, is going to be a plus c comma b plus d. Okay. So geometrically, that's what That's what addition turns into. So this guy here is A plus C, B plus D. Okay. So that's the geometric interpretation of what our addition is going to be. Okay. It turns out that there's no good way. It's actually impossible to define a good multiplication for vectors. In general, it's impossible to define a good multiplication for vectors. Right, your multiplication, you would hope, satisfies the commutative property, the associative property, and the other properties of your normal multiplication. But it turns out that it's actually impossible, except in certain cases. Okay, so what one normally does is you define sort of a lame kind of multiplication. Okay. It's called scalar multiplication. And all this means is that you can have a vector, so multiplying a vector by a real number. Multiplying a vector by a real number. Okay, so you have some vector, x1 through xn, and you multiply it by some number, alpha. So alpha is some real number. You multiply it, and what we mean by that is that you multiply every component. Okay, so you just take every component and multiply it by that number. If this number is, say, -1, then every component gets a -1 on it, right? And so, right, if your point were here, if this is your point AB, then negative AB would be the guy with the point with coordinates negative A, negative B. Negative AB is negative A, negative B. Right? Or if I say, what's 2 times AB? Well, you would just multiply all the components by 2. So you get something here, 2A, 2B. So this is the scaling. You've taken your point and you've scaled it, right? Or maybe it's better to think of this as arrows again. You take your vector and then you scale it by 2. That's why they call it scalars. Okay. Okay. So there is actually one sort of good multiplication, good general multiplication way to multiply vectors, and that's the so-called dot product. How many of you have heard of the dot product? Some of you? Okay. Dot product, so the dot product, also called the scalar product, the dot or the scalar product. So what you do is you have one vector, u1, u2, through un, and you have another vector, v1, v2, vn, and we define a multiplication on it by multiplying the corresponding components and then adding them all together. So u1 v1 plus u2 v2 plus un vn. Okay, so that's the dot product. The dot product of u1 un and v1 vn. Is defined like this. The dot product of this guy against that guy is the sum of the products of the corresponding components. Okay. And you see what's bad about this. Maybe you see what's bad about this. What's unsatisfying about this sort of product, right? you're thinking of the vectors as your generalized numbers, right? And you want some way of multiplying these generalized numbers together. And we have one way. Here it is. You take one generalized number and you multiply it by another generalized number, and you get your old-fashioned number, right? So it's unsatisfying because you'd hope that with a generalized number and a generalized number, you multiply and you get another generalized number, right? When you multiply 1 times 2, you don't get apple, right? Right? You don't get something that's completely out of the class, right? Rather, you get another number. But here you've got this product, so-called product, and it's unsatisfying because it gives you a scalar. It doesn't give you a vector. You take a product of vectors and you get the scalar. So it's called the scalar product. Okay, so it's not it's not satisfying in that regard. Okay. Just for the heck of it, let me show you what the dot product means geometrically. So this isn't really important. It actually doesn't even contribute to the rest of the lecture, but but I'm going to show it because it's interesting. Okay. Geometric interpretation of the dot product. Okay. So let me introduce a notation. The dot. Well, no. Maybe let's use dots. So this is a common notation for the dot product, but while I introduce some, I'll just write it like this: v dot u dot v. Okay, just an abbreviation. U dot v. Okay, and actually I need to make a remark. Notice that if I take a vector and I take the dot product of the vector against itself, I'm going to get u1 squared plus u2 squared plus un squared, right? But that actually has a geometric meaning. What is that? Like if we're in R2, u1 squared plus u2 squared, that has a geometric meaning. What is that?
The hypotenuse? The hypotenuse?
Yes. So it is the length, it's the square of the length of the hypotenuse. Right? So if I have this point, u1, u2, right, then this distance is u1 squared plus u2 squared square root. Right? So this is actually the what's called it's the square of what's called the magnitude, right? The size, so we call this length the magnitude, right? The magnitude, like the absolute value, basically, right? The size of the number, right? The size of this point. It's basically the distance to 0, just like the absolute value is the distance to 0. Okay, so here's the cool thing that I don't really need to show, but let's do it. U dot v actually has a geometric meaning also. U dot u has a very simple geometric meaning, just the square of the magnitude. Okay, u dot v, you got two different vectors, and you're taking their product. It turns out that it's the product of the vectors times the cosine of the angle between those two vectors. Okay, so where phi is the angle between u and v. Right, so this is u, and this is v, this is phi. Then the dot product gives you the product of the magnitudes times the cosine of the angle between them. And the proof of this fact follows from something like the Pythagorean theorem, something called the law of cosines, which is basically super version of the Pythagorean theorem. You probably saw it at some point. The law of cosine says that that if you have an arbitrary triangle, right? If this are a right triangle, right? Of course, then you would say, well, you know, if this are a right triangle, then you know Pythagorean theorem: a squared plus b squared equals c squared, right? What if it's not a right triangle? Not a right triangle, ABC. Okay. Then actually there's a relation that says this: c squared equals a squared plus b squared minus 2ab cosine of the angle opposite to c. Okay, so there's this sort of super Pythagorean theorem that can be proven using the Pythagorean theorem if you feel like it. So do it yourself. Okay. You can. You definitely can. Okay. Use Pythagorean theorem. So it's a consequence of the Pythagorean theorem, but it also implies the Pythagorean theorem, right? Because if c were a right angle, you get c squared equals a squared plus b squared, right? Because the cosine of the right angle would be 0. Okay. So it's actually the law of cosines. I said it's a super Pythagorean theorem, but in fact it's just the Pythagorean theorem, right? Because it implies the Pythagorean theorem, and it's implied by the Pythagorean theorem. Right? It's no more powerful than the Pythagorean theorem. Okay. So actually, this fact here is a consequence of the law of cosines, and so the way you see it is this. The way you see it is this. You say, what is this length here? What is this length here? Like, what do I need to add on to v to get u? V plus something equals u. Well, it'll be, I'll add on u, and I'll subtract off v. Right? V plus u minus v is u. Right? V plus u minus v is u. Or to see that maybe more clearly, this is u and this is v, and I look at u minus v. Well, u minus v means that I add on a minus v to u. Right? I add on a minus v to u, and I get this guy. This thing here is u minus v. Right? This thing here is u minus v. Right? So you see that if I add that guy onto v, I add u minus v onto v, I get u. Okay. So now, in any case, u, v, u minus v, and that gives us a relation between the lengths. That gives us a relation between the lengths, right? U minus v squared equals u squared plus v squared minus 2u v cosine of the angle between. Now I said that this is going to tell us something about the dot product, right? That this is going to tell us something about the dot product. So let's squeeze in the dot product here somehow, right? You kind of see what's going to happen, right? You see that what we're looking for is in there, right? Okay, so let's see what happens. So first off, I'm going to write this u magnitude squared as u minus v dot u minus v. Right? Okay, and then I'm going to multiply this thing out. I get u dot u minus 2u dot v plus v dot v. Oops. Oh, that's right. And one thing that I'm using is that the dot product has a distributive property. And second thing I'm using is that the dot product commutes. Right? U dot negative v is the same thing as negative v dot u. Okay. Those are true. So the dot product actually is commutative and has a distributive. Okay. And then you see the end from here, right? You see the end, right? U dot u is the magnitude squared. V dot v is magnitude squared. Divide both sides by -2, and that's the end. So, okay, so that is, so there is a way of putting a product on Rn, and that way of putting a product on Rn is has some nice qualities to it. It has some nice geometric qualities to it. Okay, even though it's not completely satisfying, because again, you multiply two vectors and you end up with something that's not a vector. Okay. Everyone all right? Everyone all right? Questions? Okay, so it turns out, however, that for R2, there is a good way to put a multiplication on it. There is a way to put a multiplication on it that satisfies everything that you would want, right? It's associative, it's commutative, it does everything that you'd like it to do. So R2, it turns out that R2 is special. R2 is special. You can put, one can put a good multiplication on it. Okay, and it turns out, so the way to do it is this. You say, we're going to define the product of two vectors in R2. Okay, so here it is. Here it is. The product of two vectors in R2, we're going to define it in the following seemingly peculiar way. XX prime, so xy times x prime y prime is going to be xx prime minus yy prime, comma, xy prime plus x prime y. Right, so for example, if I had 1, 2 times 3, 4, I would get xx prime minus yy prime, xy prime plus x prime y, right? -5, comma 10. So I'm sorry to do this. I'm using the dot in a completely different sense now. Okay, previously the dot was the dot product. Forget that. Okay, we're not going to think like that. We're not going to use the dot product anymore. We're introducing a different kind of multiplication. Here it is. Okay, xx prime minus yy prime, xy prime plus x prime y. And maybe some of you can see what this is already, recognize what this is already. Or for example, if I had, say, 2 comma 0, 2 comma 0 times 3 comma 0, what would happen then? Well, I would get xx prime, that's 6, minus yy prime, that's 0. Xy prime is 0, x prime y is 0. So I get 0 plus 0. That's going to be 6 comma 0. Right. Is that okay? Is that okay? Right. If I take, so for example, if I take a point x comma 0 and I multiply it by another point x prime comma 0, x comma 0 times x prime comma 0, by this rule is going to be xx prime xx prime minus yy prime 0, xy prime 0 plus this. Right. Right. I multiply x comma 0 times x prime comma 0, I get xx prime comma 0. Okay. Okay. Everybody okay? Okay. So let me just note, since I did that, let me just note that you can think of R being embedded, R with its usual multiplication, usual addition and multiplication being embedded inside R2 with vector addition and this new multiplication. What I mean by that is that, wait, hold on. People are coming. What I mean by that is that if we think of this line here as R with its normal multiplication, right? That multiplication turns out to be the same thing as the new multiplication, right? If we consider this point to be on the real line, on the real line, x prime, and we multiply them together, we would get xx prime, right? And here, if we think of this thing as being in R2 with the new multiplication, and we multiply them using the new multiplication, the same thing happens, right? x0 times x prime 0 gives us xx prime comma 0, right? So, the new multiplication constrained to this real line here basically looks exactly like the old real line, right? And if we added things using vector addition here, it looks just like addition from on the real line, right? So if we use vector addition and the new multiplication and somehow pretend that we don't see anything other than the real line, we can't tell that this is any different from R, right? Multiplying, it looks like just like multiplying in R. Adding, looks like adding in R. So R sort of lives within R2 in a very real sense. Okay. 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 So other things to notice. So observe that if I have 1 comma 0 times y. Then I get 1 times x minus 0 times y. I get 1y plus 0x. Right? In other words, I get x comma y. Right? In other words, the number 1 from the real line, the number 1 from the real line is the multiplicative identity for this new multiplication. Right? You multiply anybody by the number 1 comma 0, and you get back the thing you started off with. So we have something. This is the this is the multiplicative identity of the analog of 1. Right? This thing works as a 1. Okay. And then other things that happen for the real line also happen here. So it turns out that you have commutative, right, that if you change the order, it doesn't matter. If you multiply, three vectors, one vector times another vector, and then times a third vector, you've got associative property, etc., etc. Okay, so all the nice properties that you liked, that you wanted, actually turn out to work out. Okay, so R2 turns out to be very special. Okay. Another thing to observe also is if you take 0, 1 and multiply it by 0, 1, by 0, 1, then what do you get? Can anyone tell me immediately what you get? So you're going to get 0 times 0 minus 1 times 1, right? Then you get 1 times 0, 0 times 1. Right? In other words, you get negative 1 comma 0. Okay. So, right? And this is the real punchline, which is that in R2 with the new multiplication, there is a square root of negative 1. Okay. A square root of the real number negative 1. Right. You have something that multiplies. When you multiply it by itself, you end up with negative 1, 0. Right? Negative 1, 0, which is your old friend negative 1 in the real line. Okay, right? And so you know what this is, right? People call this point 0, 1. They call it I. Right? They call it I, the imaginary. Right? The square root of negative 1. Yeah, I was tricking you all along. Okay, at least that worked. Okay, so right, so what, right? So whenever this x comma y, you could rewrite it as x times 1, 0 plus y times 0, 1. In other words, x times 1 plus y times I. Right? X plus y I. Right? That's maybe how you're more used to seeing it. Okay. Right? X plus y I. X times x comma y. Right? And if you have x plus y I times x prime plus y prime I, you know what you get, right? You're going to get x prime minus y prime oops, xx prime minus yy prime plus xy prime plus x prime yi, right? Which is the multiplication. Which is the multiplication that we've been talking about, right? X prime minus y prime, xy prime plus x prime y. Okay, so okay, so you know, just some definitions, right? Given, right? So we call R2 with vector addition and the remultiplication C, the field of complex numbers. Okay. Some things that you've probably heard before. If xy is in C, we call R the real part of xy. We call y the imaginary part. We call x negative y, that's to say x minus yi, the complex conjugate of xy. Complex conjugate. Okay, so if this point is the complex number z, if this point is the complex number z, then we call this point the complex conjugate. X negative y is called the complex conjugate, and it's denoted as z bar. So you put z with a bar over it. That's the complex conjugate. Okay, and notice that if I multiply z by z bar, like xy times x negative y, maybe I'll write it in the more standard way, x plus yi times x minus yi, then you get x squared plus y squared. Right, because you're going to get x squared, you're going to get a y squared times negative I squared. Right? And negative I squared is just 1, so you get y squared, and then you get this plus that, which is 0. Right? xyi minus xyi, 0. Okay. So this is, you remember, this is actually the magnitude of xy squared. So we write that we call this thing the modulus of z, but it just basically just means the magnitude. Okay? The magnitude of z. The magnitude of z is going to be z bar to the 1/2. Okay. The point is that we have a way of talking about the size of these numbers, just like we talk about the size of real numbers. Okay. We have the absolute value, right? Absolute value, we have something like the absolute value. It's basically the absolute value. Okay. Okay, so since we can talk about size, we can talk about convergence, right? We can talk about power series, we can talk about radius of convergence and this sort of thing. Okay, but I think I'm going to stop here. We'll talk that. We'll get to the more interesting part next time. So let's stop here.